Oh, yeah, here we go into lesson 4.2, known as approximating area with Riemann and trapezoidal sums. It's nothing short of the sweetest thing ever, and it's actually relatively simple. We're going to use a lot of very basic geometry to rock and roll through finding the net signed area. Between a curve and the x-axis, which is kind of weird. All right, so what's that all about? Well, when you're finding the net signed area, signed means that area can actually be negative. It's true, it can be. And the net area means the overall area, combining both positive and negative areas. So I want to show you what this basically represents. Let's say that we're looking at a curve, right? Here's some curve, whatever it is, some graph, and we want to approximate the area. So we're literally finding the area here and the area here. But any area that is above the x-axis, between the curve and the x-axis, is considered positive area, and any area below the x-axis is considered negative area. The reason being is, if you think about this, let's say that this curve represents, I don't know, velocity. Well, if I find the area between the curve and the x-axis, we've seen this before way back when in chapter 1, that the area represents the position that has changed, or the change in position, otherwise known as a displacement. So if you've got velocities that are all positive, we're gaining, right? Whatever we're gaining in. Maybe we're moving to the right, or maybe we're moving up. We're going in the positive direction. So that positive area means we've accumulated a positive amount of position. But the negative area means the velocity here has been negative. So we're going backwards or to the left. Now, if you're sitting out there saying, yeah, I'm not really getting the whole velocity thing, don't need to know that in my calculus class, then all you need to remember is area above the x-axis is positive, area below the x-axis is negative. We would add those two areas together, and that gives you the net, the overall signed positive and negative area. So that's our goal. We want to be able to approximate that. Okay. From here it says, how is finding the area between a curve and the x-axis related to distance equals rate times time? Well, we actually looked at this in great detail. Again, if you need to check out those videos, it's one of the first videos we did way back when in chapter 1 at the onset of calculus. So check that out. Pretty cool. But we're going to go over a quick review of this. Well, if we take a look at distance equals rate times time, what I've given you is a velocity graph. So this would be the rate, how fast something is going and the direction it's going in. So it appears we're going at 30 meters per second at a constant rate. And we're going over a time span from 0, I'll put a 0 there, to 10 seconds. So let's think about this. If we find the area between this curve and the x-axis right here, in this case it's the t-axis, we'd basically be finding the area of this rectangle. Well, the area of a rectangle is not hard to find, right? We just need this length here times the width, or the base times the height. So area equals base times height. And if we take a look at that, that's equal to the base, that would be this. That's a distance of 10. Now in this case, that's 10 seconds. Now I'm going to put that in two different, I guess, orders here. I'm going to put the 10 second, and you might be like, what, why? The height's there. You'll see in a little bit. So 10 seconds is this overall width of the rectangle. The height is 30. And it doesn't matter what the base or the height is, by the way. This can be the base, that can be the height. Doesn't matter. Overall, these units are meters per second. Oh, check it out. When we multiply this out, we get an area of 300. And that's cool. But what's the importance of this? Well, look at meters per second times seconds. The seconds cancel, and you're left with meters. Wait a second. Let's take a look at the distance equals the rate times the time. Well, the rate in this case is 30 meters per second. There we have it. It's exactly what we just calculated. And the time, the amount of time that's gone by, is 10 seconds. And that will give us our distance. It's distance because we're going in one direction, right? The velocity is positive the whole time. 30 times 10, as we saw before, was 300. The seconds again canceled, and you're left with 300 meters. So I hope now you're convinced that the area between the curve and the x-axis, found by simply just finding the area of this rectangle, is the same as, or can be related to, in a lot of cases, to distance equals the rate times the time. Isn't that beautiful? I think so too. In the next few videos, we're going to go over things called Riemann sums. They're ways of approximating areas of curves where the curve's not nice and flat and does not form a nice rectangle. I'll see you there.